Any questions to start with?
Maybe a very basic question.
Yeah.
Like last time we had this derivation, the projection-based derivation, where I think effectively you kind of claim that PA PB hat PA is
Ah,
equal to PB hat PA. I'm sort of skipping a couple of steps.
okay, let me go back to that page. Yeah. Sorry. In this proof, right? You are talking about this proof?
Yeah.
Okay.
So when you want to, before you use the, at the point that you go from the norm to the Frobenius norm,
Uh-huh.
we have this thing where PA PB hat PA equal to, yeah. So you have the stars can be removed safely. I think that's fine.
Okay.
So then it comes down to PA PB hat PA. PB hat PB hat. I don't know. I think that seems reasonable.
It's PB.
Yes.
You are projecting twice in Fourier space. Projections always have this PB projection square is itself.
The thing is, PB hat is more than a projection, though, right? Like
it is a projection. I mean, so okay. What is projection? Projection is any operator having this. Okay. What is? Yeah. So let me write here.
yeah. Sorry, maybe it's obvious to everybody, but I
No,
just
it's
yeah.
fine. No, we'll address this point. So what is PB hat? PB hat is you take a function. I mean, so what it does is it takes you take a function, go to its Fourier transform, then restrict it to its the set B, and
Exactly.
then go back to the inverse Fourier transform via the inverse Fourier transform. So this entire operation is what we call PB hat, right? So this is so if you do it twice, what happens? Suppose you do it twice. Well, you come back here. You have a fat indicator B checked. You apply its Fourier transform. You get a fat indicator B, right? You multiply it again by indicator B. Nothing happens. There's
Nothing
already
happens.
one indicator.
Yes.
And then so it is. It's exactly the same. Okay. Go ahead. But you had further question here.
No. This makes sense.
So this is why PB hat square is PB hat. But did you have a question also about PB? So the other PA, this becomes PA. This is PA. So this one now PB square becomes PB. I mean PB hat, PB, and then PA. And because of the trace, I transferred PA to here. It's not that I said PA, PB hat, PA equal to PB.
Oh, I see. Okay, that was a missing part. Okay, got it.
Trace of XY is trace of YX. So I transferred the PA. That PA square again is PA.
Understood. Okay, that was what I was missing. Thank you.
Okay. Any other questions?
Yes. Why is PA star equal to PA?
Oh, PA. I mean, it's a indicator, right? So PA F is just F times indicator A. So PA F G is just F G bar indicator A, right? Which is same as if you want F G indicator A bar. That so which is okay.
Okay, yeah, done.
Yeah, so see, generally this is the definition of a projection operator, that it satisfies, it is self-adjoint and idempotent. And it is clear, I mean, in these cases, okay, this is the check that I gave, but what for especially PA is just you're restricting the coordinates. It is if you were to think of functions as vectors, you're just setting 0 on many coordinates. That's the basic projection that we know. Okay, that's the most basic projection we do, where we take, say, you are in R10, and then you just restrict to 5 of the coordinates and get a mapping. So that is the kind of projection. And PB hat is also restriction, but in Fourier space. So you kind of you do and then come back. It's a similarity transformation of the of a restriction. in Fourier space. So you just conjugate it by Fourier transform. Any other questions? Okay, if not, let me come back here. So let me recap quickly what I did last time. So I took G equal to Zn. I did some notational confusion, all unnecessary. But basically the point that I proved was that if f hat is supported on, let's say, if we know f is band limited in the sense that f hat is supported on some frequencies minus r to r, where everything is interpreted modulo n, right? Then we can write f hat of d as square root of p over square root of q, j equals 0 to q minus 1, f of jp, chi d of jp. Chi d is this complex exponential. All that is fine. So where and d is everything from minus r to r. 1 second. Yeah. So minus r to r. In other words, all the Fourier coefficients f hat of d, these are the only non-zero coefficients. They can be recovered from the values of f at multiples of p. Can recover f hat and hence f from f of jp 0 less than equal to j less than. So by sampling f at regular intervals, you can recover f hat. And so that's the, as I said, for those of you who have seen the continuous version of the Shannon-Nyquist theorem, this is the discrete version. I mean, in some sense, there can't be any magic. So functions which are supported, whose f hat supported on this means that the dimension of that space is 2r plus 1. And okay, by the way, q here is assumed to be at least 2r plus 1. Okay, so and if you are sampling f at values multiples of p, then there are how many multiples are there? There are at least q multiples. There are q multiples, and q is at least 2r plus 1. So you have the right number of parameters to recover. That's the way to always check that if you have the right number of parameters to recover all the functions in the space. If your dimension is, you can't recover a higher dimensional space from a lower dimensional space. So that is not possible, but here that's all. So this is one type of recovery problem in signals. But what you can observe here is that in some sense, I don't know the practicalities of it, by the way. I am very far from real applications of any kind. So if you, for a moment, suppose you know the signal f, or you observe the signal f. Of course, you will observe maybe with some noise or something. Then what you get is some noisy signal. But here, what happens? You are basing everything on f of jp. Suppose this q is small. Suppose assume q is small. That means there are only, let's say q is 5 or something. There are only 5 values of the function. Okay, 1, 2, 3, 4, 5. Based on only 5 values, you are reconstructing everything. You see, then if n is large, then p will be p over q is like, I mean, this is n over q, right? So this ratio will also be large. So any errors that you make in this observation f will also get amplified by this. Apart from, even if you are doing exact calculations with this complex exponentials, even if I assume that, any errors that are made in the observation will get amplified by this also. So it's I don't know what is the there must be some study of how robust this is and such things, which I don't know about. Okay, but I'm just mentioning that that is a kind of thing. So now I'll move on to another signal recovery problem, which is a slightly different one. I can just start here itself, I think. So here the signal recovery is of band limited signals. Okay, so again, so yeah, so 1 second, what is the exact phrasing? Let me look up, I forgot that. Yes, so recovering a band limited, okay, is it? Oops, sorry, I lost the window. 1 second. So recovering band limited signals from incomplete So in some sense, the way at least I am thinking of it is the following. So let's say our signal, again, we are working on Zn. Everything here will be on Zn. And we have a function on it, which is our signal. Okay. And the objective is always to recover that signal. So again, here another type of kind of maybe possible delicate nature of this previous recovery problem is, suppose you are not observing, you are observing not at every point infrequently, but these use the exact multiplicity. Okay, it is at 0, p, 2p, 3p, and so on. Suppose it's not quite like that. Maybe every week you observe once, but you forget on Monday, then you observe on Tuesday, and such things. Then these are not exactly multiples of p, but slightly off. So in such case, can you still recover? Okay, so that seems, yeah, at least that is not addressed by this kind of thing, right? So that sort of issue is being addressed here in some sense. So what do we observe? So assumption, okay, first let me make the assumption that it is band limited. Well, f hat is supported on some b, on some set b. Okay, so well, if b is of the form, what I have in mind is actually this. I don't know whether anything else comes up in if there's in realistic situation, I do not know. If b is like this, we say f is band limited, right? Meaning that it has only low frequencies. So, okay. So suppose we have some assumption like that. Actually, the whole analysis, I will not use that B is like this. Okay. But I don't know if the part of the content of these theorems come from whether the assumptions make any sense in real life, actually. And this type of assumption may make sense in real life. I mean, so when you, I mean, some things are I mean, if you are having some musical signal, maybe there is all the frequencies you are here are in some interval and stuff like that. So maybe it makes sense. So anyway, so but f hat we assume is supported on some set B, which is contained in Zn hat, which we also identify as 0, 1 up to n minus 1, right? So B is also a subset of 0, 1 up to n minus 1. Now, what do we observe? We observe most of the places we don't observe always. So what we observe was g of k. Okay, for k equals 0, 1 up to n minus 1. But what we observe is actually we do observe f of k. And if k is in, for some reason, we'll write like this. If k is not in A, we observe it. And if k is in A, we do not observe it. And we will, in addition, assume that there is actually some noise here.
What is A? You mean B or?
No, this is a different set A. So B is some subset.
Okay.
And here you are making observations. A is another subset of 0, 1 up to n minus 1. So for example, I mean, in the previous case, the assumption was that f hat was supported on minus r to r, b was this, but the where did we observe it? We observed it at multiples of p. So in some sense, that a complement is this multiples of p. That's where we observe. But now, two additional things that is not assumed to be some arithmetic progression like that. And second, we are not observing it exactly. There is also noise. So now,
are we taking the band limited assumption that B has a small support near 0 or whatever?
No, we are assuming f hat is supported on B. And when, I mean, what I got here was that when B is of this form, it makes sense to use the word band limited. If it is some arbitrary subset of 0, 1 up to n minus 1, okay, you can, I don't know whether to call it band limited or what. Usually band limited means no high frequencies. So I will just not use that word much. I mean, occasionally I may use, but I will say f hat is supported on B. Of course, some assumptions on B and A are required. If B is the whole set and A is the empty set, then we can do nothing. Right? So there is nothing that we can do. Of course, we need. We are happier if B is smaller. That puts more restrictions on the functions possible. And if we are happier if A is larger, then we have more observations. And we are also happier if n is small, then the noise is small. So n is some noise. Okay, so goal is again to recover the signal to the extent possible.
So Manju, that means so we are only assuming that A and B satisfy the uncertainty principle. What is the essential minimum? That's all you're assuming.
Well, I have not assumed yet. I mean, I will come. I have no conclusion yet. So I don't. So I have not made any statement yet.
Okay.
Yeah, but
No,
when
but
it comes, exactly what you said sort of will come. That we cannot. Sorry, we would like. I said we would like A to be large. I take back. Okay, so your statement reminded me. We observe on A complement. Therefore, we would like A to be also small. Actually, because we observe A complement. So then more observations if A is small. Yeah, what you said will come, Kaushik. But I have not yet made any statement. So our goal is to recover F or estimate it as well as possible.
okay.
I will make the statement. So is it possible to recover? Well, for one, let's just consider, suppose the noise is fixed. So toy case. Actually, not really. Both are. It's not very. I mean, it's also a reasonable case. Suppose n is known. Then you may as well subtract and set it equal to 0. Okay. I mean, it doesn't matter. If n is known, then you can just set n equal to 0.
So Manju, can you use a different notation? You're using Zn also and n also.
Okay. Yeah, you're right. You're right. So noise. What is so electrical engineers here? What is used for noise?
Error E maybe.
E. Okay. E sounds. E or epsilon maybe. E are used for complex exponential. Let me call it epsilon of. Yeah, that is in statistics, that is common. Okay, so let me use epsilon for that. Suppose the noise is known, in which case we will have subtracted and set it to 0. Okay, so no problem. We'll assume epsilon equal to 0. Then what we have is this. Then we get G equal to F indicator A complement. Okay. So question is, can we recover? Okay. So suppose can two signals give the same? So recovery is same as asking whether the mapping of F to G, okay, signal to observation, is injective. If it's injective, that means you can recover the signal. Whether you can, how you recover is another question. That's a practical question of importance. But just theoretically speaking, the statement that you can recover a signal from observation is just a statement that the mapping, the transformation that takes the signal and gives you the observation is an injective mapping. Okay. So if not injective, what does that mean? If not injective, then there exists F1, F2 such that F1 indicator A complement equal to this G, or we can remove the G. So two signals get mapped to the same observation. So F1 indicator A complement is equal to F2 indicator A complement. But also my signals are coming from the collection that I am assuming, right? So and F1 hat, F2 hat, I assume they are supported in B. So is that possible? So in other words, so let's see, let's look at F1. So you put H equal to F1 minus F2. So then what do we have here? If H is F1 minus H2, then H is 0 on A complement and H hat is 0 okay, on yeah, so on B, right? Okay, actually something is a bit fishy. Hold on. Right, actually, yeah. So if this is true, then H hat is 0 on B and H is 0 on A complement, right? Is this correct, or am I making a mistake?
Why is H hat 0 on B?
Yeah, sorry, that doesn't make sense, right? Sorry, no. Supported H, yeah. So H hat is 0 on B complement, not on B, yeah. Both F1 hat and F2 hat are 0 on B complement, so H hat is 0 on B complement. Is that okay?
Still, can we say that? I mean,
no, H hat is just F1 hat minus F2 hat, right? And F1 hat is 0 on B complement, F2 hat is 0 on B complement.
right.
Is okay? I mean, so both these functions are 0 on B complement, so their difference is also 0. So that's all I'm saying here. Here, H is 0 on A complement because F1 and F2 agree there. So what this is saying is that the support of H is in A and the support of H hat is in B. Now, like Kaushik said, this is leading us to the uncertainty principle. So if cardinality A into cardinality B is less than n, I am using small n here, then H must be 0. Implies injective. So signal recovery is possible. Okay, so that's all. Is this okay? I mean, so this. Go ahead.
So here the noise epsilon depends on f. Or?
No, the noise is no. I mean, it depends. No. The noise, noise is something completely different.
Independent.
What do you mean by independent? Sorry.
So so you're defining G for any such f. So the epsilon is fixed, is it? Or are you?
Yeah. So epsilon is external to the problem. Yeah, if you want to assume like that, yes.
Okay.
Epsilon is, see, it's not somebody who sees the signal and then introduces noise.
Okay.
So if that could be done, then you can imagine somebody adversary making the noise equal to minus f. So then observation will be just 0. Okay. So that's not, I mean, I think those kinds of problems are also studied, but this is not that. There is no adversarial choice of the noise. The noise is just not depending on the signal. Any other questions about this? So what we have argued is that this problem is actually solvable. So this is what I was once referring to, that uncertainty principle is saying things cannot be done in some way or another. But in a nice way here, it is telling us you can do something nice. If using uncertainty principle, we are able to prove that signal recovery is possible. Okay?
No, I asked that because I mean you wrote the map is not injective, right? That's where the problem comes from. So if the map f to g, the signal to observation.
No, it is injective. Is what
Right. Yeah, I mean that is the problem. So if you're sending if you're sending f1 and f2 to the
epsilon is fixed by somebody.
So right. So f1 goes to f1k plus epsilon k, right? In the observation thing.
Yes.
So the difference will just be f1 minus f2, right? 1k complement. A complement, sorry.
No. I'm saying that here I'm assume that epsilon is known.
Okay. So there is no noise in this whole thing.
Yeah. So there is no. Okay. That's why I set epsilon equal to 0.
Yeah. Sorry.
If epsilon is known, I can subtract it.
Okay.
Yeah. No, you are right. Okay. I should have answered that part. Yeah. So here the noise was not there. So it's f1 indicator. I mean f1 on a complement and f2 on a complement. So if the observation is the same, then f1 and f2 agree on a complement. That's what I would. Any other questions? Okay, so now we will do a more serious type situation. All this, by the way, I'm saying from the paper of Donohoe and Stark. I believe it's a famous paper and there is enormous amount of follow-up papers. I don't really know the literature or anything, but the original paper is quite nice. And so Donohoe and Stark, and it's called Uncertainty and Signal Recovery or something like that. I will put it on the Teams app. So remind me if I forget. Okay, if I forget, remind me on Friday.
So basically, if two signals sound the same on some set, then they must be same. That's what we're trying to say here, right?
Well, if you
choose A.
Somehow. No, there is assumption on this type of signals.
Okay, that's also
signals of this kind. You see, a priori, if a priori without any assumptions, if you don't observe a signal at one single point, then you cannot recover that. I mean, you cannot do magic. So if your f is on 0, 1 up to n minus 1 and you don't observe it at one point, f of 1, then that's lost. You can do nothing. But if you have some structural assumption in f such that f hat is actually supported on maybe only half n minus 5 points or something, then you can actually use that to recover this missing information.
Okay, yeah, sorry, yeah, go ahead. Yeah.
Okay, so now let's do a more serious case. So the claim, of course, when there is noise, you don't expect to recover f exactly. There will be noise. So you want to estimate it reasonably. Okay. So the kind of theorem that I want is like this. Should I write the theorem or should I just derive it? Okay, I'm thinking. Okay, let me just write the theorem. I'll have to look it up. Assume that size of A into size of B is less than n. Okay, and then let Q be I minus. I had PB had PA, right? Now I will have PA PB hat. I don't think it makes a big difference, but the inverse. So that one of the points is that it exists, and no, and so let's define this Q like this. So the claim is this Q can be used to recover F. Okay, how? If I take Q, I take apply. This is a linear operator. I apply it to G. That will give me something very close to F. Not, of course, it can't be exactly equal to F. So I'll say that this is bounded by a certain constant, which depends on this A and B. And it also depends on N. So let me just call it C here. So a certain constant times the norm of the noise, which is what I called epsilon. Everything is in L2, where this constant is something like it depends on how well this is satisfied. So it is 1 over. So this is the measure of how good that is. Mod A, cardinality B over N. It is the square root of that. So the closer, I mean, if it is not, if the cardinality is close to N, then not good. I mean, then this constant is large. You see the way, I mean, so for math students here, so the concepts that we use in mathematics, the way they show up in this, it's actually quite nice. I mean, we talk about the norm of an operator, the boundedness of an operator and stuff. And that is actually important in the following sense that if this is the bound we have for this operator actually I minus q. That's what we are basically saying. And it's telling us that our signal recovery is good. It is actually, of course, if the noise is 0, it may be good, it may be exact, but otherwise it's not exact. But we can do within a factor of the how big the noise is. Okay, assuming noise is something small, then you can the difference from the signal to your recovered estimate is only a constant blow up of the noise in this norm sense. That's what the statement is. Okay, so this is actually quite a robust statement. So let's see the proof of this. So this itself is a statement of signal recovery. Okay. Okay, so how do you prove this? So why does Q exist, by the way? This is a simple exercise in basic linear algebra. So anyone? So why does Q exist? So we proved something about this. Under this, what did we prove under this condition? Well, we proved for PB hat PA, but the same holds for PA PB hat. Either get it from there or prove it again. So when it's less than n,
the norm is less than 1.
the operator norm is less than 1, right? Oops. So this is the operator norm, okay, is less than 1. Okay, so now does that remind you something? So if the operator norm is less than 1, I am saying that I minus that transformation is invertible. Do you know why?
The kernel will be trivial, kernel of the thing in the bracket.
So this I minus, right, you can say that. So one way to say it is, see, if norm t is less than 1, then you take I minus t applied to any x, it will be greater than identity applied to x norm minus, okay, it's greater than equal to norm tx, but since this is strictly less than 1, so this will be strictly bigger than norm x minus norm x. So it is strictly positive, so it is never, so I minus tx is never 0. Which means that I minus t is, we are working in finite dimensional setting, everything is finite dimensional, so this is I minus t is invertible. So in fact, you can get it's a useful point to know that you can in fact write a formula for the inverse, which is the familiar geometric, I mean, what is it? Formula for the geometric series. So in fact, this is what it is. See, if t was a real number with absolute value less than 1, you know 1 plus t square, etc. would be 1 over 1 minus t. And absolutely the same thing is true if it's an operator with norm less than 1. Okay, very useful, and I mean, it keeps coming again and again. So, so this is something that is useful to know. But I'll come back to this later. For now, it is less than 1, and hence I minus PA PB hat is invertible. So all I need to know is, okay, so I mean, so all this is under the previous assumptions only, right? Okay, so F hat is supported on B and all that. Okay, I haven't written that here. So now let's take, so let Q be. So now it makes sense to write I to be, Q to be this inverse. So what is F minus QG? That is the question. So first, what is G? So note that what is G for me? G is this, right? So G can be written as, so let's just write as F. You can write it as G as PA of F plus epsilon. Or I mean, epsilon can be set 0 outside, so you can write PAF plus epsilon. I don't know which one I want to write. Yeah, so let me write PAF. epsilon is anyway 0 outside of A.
No,
Okay.
Manju, is it PAF? Because PAF is F indicator A, right? And you are putting
You're right. It's not PA.
I minus.
I minus PA. Plus epsilon. Is that okay? So it is not PA. We observe it on the A complement. Okay. So that this is the reason. So the only reason I did that weird thing of doing on A complement, which is what Donohue and Stark also do, is that finally I got it in the usual form A into B. That's all. Cardinality. That's the reason. So G is I minus PA times F. On A complement, we do F plus epsilon, and outside we get 0. So that's what I have written. Epsilon is assumed to be 0 anyway. So this is without loss of generality. I mean, anyway, you know where you are observing. So where you are not observing, you don't have to take noise into account, right? So you don't observe, there is no noise either. Okay, so this is what it is. But one thing to notice is that what is the assumption on F? Assumption on F is that it is band limited to B. So that means if I apply PB hat to F, so actually, let me say that this is, okay, so no, I don't want to put PB hat there. Let me just write it like this. So why? Because so what do we have? Everything is the same except instead of PAF, I have PA PB hat F. But that is because PB hat F is F. By assumption of band limited, whatever. I mean, we are assuming that Fourier transform is supported on B. Therefore, PB hat F is F. So this we have this. So this is now pretty much you see, right? I mean, so what? So this is, so in other words, now if you apply Q to this, Q is the inverse of this. So you get F plus Q epsilon. That's all. And we are done. So F minus QG is norm, if I want, is norm of Q epsilon. Okay, minus Q epsilon, both have the same norm, which is bounded by L2 norm of Q times, sorry, this is operator norm of Q times epsilon. L2 norm. Okay, what is the bound we have? Okay, so not only is there, what is the bound for the operator norm we had? So we also showed we actually showed it for PB hat PA. So you show the same for PA PB hat, either directly following the same steps or you get it from there. I don't know, whichever. Okay, so we showed that this is less than equal to the Hilbert-Schmidt norm of the same thing. Or the Hilbert-Schmidt or Frobenius norm, which was in fact equal to square root of cardinality A into cardinality B over N, right? So what we have here is that, so Q is what is, okay, by the way, what is going to be I minus Q bound? So this means, so what is the bound on the norm of I minus T inverse? This is also something useful to see. If let me use this formula, the geometric formula is less than equal to the sum of the norms, but the sum of the norms will be identity has norm 1 plus sum of norm of T is that norm of T square is at most norm T squared plus so on. Okay, but because so one of the things is norm of Ts is less than equal to norm T into norm S. If you do not know this, just follow the definition. Norm T is by definition you are maximizing, you are taking the sup norm of T on the unit ball. So T and S, they are all operators on some Cn, let us say. So then T is the norm, operator norm of T is the sup norm on the unit ball of Cn. And you are composing two of these things. So sup norm, you can see very easily, will be bounded by the product of the sup norms, because this will be T of S of X, where if X, yeah, anyway, so it's very easy. So but this is 1 over 1 minus norm of T. So from this, so we will use that. So we will say similarly, first of all, PA PB hat is what we have here, is less than equal to is this correct, what I got here, or is it not correct? So in which case, norm of Q will be less than equal to 1 over 1 minus this, right? Actually, what I wrote was slightly wrong then. Okay, so anyway, this will give me, so this is my constant, okay, C times, so this is the constant C times epsilon, except the constant C I got as square root of 1 minus, but it looks like it is 1 minus square root of, okay, I will check this point and correct it in the notes, okay. So it looks like it is 1 minus the square root, and but none of the interpretations I gave have any need to be modified, so it's all fine. So it seems this is the bound for the operator norm that I have. So that's the end of the proof. Any questions about this? So it's a nice proof. I mean, so no single proof here is too complicated, but it doesn't have to be. The point is it's quite insightful, and what you have is that if you have a band limited signal which you observe at a reasonably large space, so subset, then you can nearly recover the, and even if there is noise, you can nearly recover the signal like this. Okay, so practical recovery was also implicit here. You just have to apply Q to G. Okay, and again, I am not a person who has done much I do simulations and so on, but I don't do numerical analysis, so to speak. So but people who do seem to feel that, I mean, so inverting is a complicated thing, but this type of thing is much easier because it's basically iterating. So Donohoe and Stark remark in their paper that that is in fact a good way to recover the signal. So numerically, recovery can be done you start with, let us say you start with the observation. Okay, so how does it look? I mean, so your space is there and the observation is only on some subset. Okay, so you have some observations. Restricted to some subset, and outside you have not observed anything. Now what happens? So that is what your G is, because this is a complement where you have observed and you have this is supposed to be the signal. So then you apply F1, which is you just this is basically this iteration. Okay, so it is G plus PA PB hat F0. Okay, And then you keep applying keep doing it like that. So if you follow these iterations here, basically they will give you this. F2 will be G plus PA PB hat F1 and so on. So in general, Fk plus 1 will be G plus the observation plus PA PB hat Fk, whatever you have reconstructed. So so you see there is the second part is always PA times something. So that is 0 on A complement. So this part is my A complement, right? So this is where the original observation is. So there I am always, the signal is always going to remain as G. I mean, my estimate for the signal will remain as G, nothing else. Whatever I observed will be my estimate also. But elsewhere, what happens, F0 is just like this. But when you do F1, it will take this G and apply this to F0. So it will start sprouting some hairs here. Maybe it is 0 on some parts, and then it will keep modifying it slightly this way, extend something, do this, whatever. And it slowly starts recovering the signal. Of course, we are not saying it will exactly recover. In the end, what should you get? I mean, if you remember your fixed point theorems and so on, in the end, you get with a fixed point solution to, I mean, I shouldn't write F, so let me just use a different symbol. So when you keep iterating and fixed point are very closely related things. So that's a recurring theme. So you will finally, if you keep doing that, these things will converge to whatever will solve the fixed point equation, namely H equal to G plus PA PB hat H, which if you transfer this to the other side, you see exactly it is saying that I minus PA PB hat H is G, or H is Q times G. Q times G is what it will converge to. So, or it will converge to that particular solution, which is assured to be reasonably close to the signal. Is okay? Any questions here? So this is the signal recovery problem that one of them I wanted to talk. Actually, there is another one that is there in Donoho stack. I am completely confused about it. So I just wanted to mention it and ask if somebody is interested in reading it and then explaining to me, because I got slightly confused about that. So do I have any time? Okay, it's 12:57. Maybe let me describe the problem. Next lecture, I will not talk about it. Next lecture, I will move on to a different topic. I will go to Fourier analysis on Z2 model, Z2 to the N, and a problem of social choice. Okay, it's an interesting problem, completely different. Okay, before that, are there any questions here about this? Okay, if not, then let me mention this other problem. So that problem is, it's called, I will tell you, it is called. So another problem in Donoho and Stark. Okay, by the way, that this we are not, actually I'm not going to be discussing this. So people actually may also leave the lecture now, because what I'm now saying is something that if anyone is interested in looking at their paper and then explaining to me, I will be happy. Okay, it's not that I followed the math, but what my confusion is slightly different. Recovering a sparse signal from narrowband observations. Okay, here apparently what they say is the following. Sometimes the signal, so this is narrowband observations of a wideband signal, by the way. So which means that f is no longer band limited here. Okay, f is not band limited. F hat is fully supported. Okay, so that's what wideband means. No restrictions on so it is fully supported. So, but what happens apparently is that the very nature of observation sometimes makes things band limited, meaning there may be a lot of noise in the air, but you can hear only up to whatever.
It's 1 o'clock.
Up to some whatever, I forget how, so many to so many kilohertz or whatever that you hear. So the ear can hear only so above that you cannot hear, right? So like that, you observe signals via some instrument, and apparently that itself limits the frequencies that you can see. So the observation here is so the observation that one has here is the following. Let me just yeah. So you are. I mean, so what you get is what you see is some. Let's say you are measuring Fourier coefficients only, but you only measure Fourier coefficients if they belong. You measure some Fourier coefficients, but many Fourier coefficients get filtered out because they are too high or something like that. So if k is maybe I should say if k is not in B, just to make it symmetrical. Yeah, k is not in B, and 0 if k is in B. So maybe B here should be thought of as outside of -R to R. So if high frequency, then you don't observe it. If low frequency, you observe the Fourier coefficient, but maybe it is also corrupted by some noise, which I will write as epsilon hat of k. So what you see is this H. So this H is the observation. So problem is again recovering F. But okay, what takes the place of this? What takes the place of this band limited assumption? So the assumption they make is that F is sparse. That is, so F is supported on some set, which is maybe we call it A. F is supported on some set A. Okay. So this happens in many problems actually. Many signals are sparse. I mean, it's not like so. Yeah, this is reasonable, but so and then they go on to address this problem. So F is sparse, and what you observe are this thing, and then how do you recover F? Okay. So they analyze this, and I can go through the analysis, but what I'm totally puzzled about is why it is not exactly the same problem and what actually is the difference. Meaning it looks to me exactly the same problem as F and F hat reversed. Okay, the role of F and F hat appears to me to be reversed. Instead of F hat being supported in a small set, you are assuming F is supported in a small set. And what you are observing, it seems to me exactly the with F and F hat reversed. And since anyway you go from the way you go from F to F hat is almost the same as the way you go from F hat to F. You just take the check, right? So I don't understand why you can't exactly invoke the same theorems and get it. Today morning I was trying to do it, but I could not figure out. So anyway, I abandoned it. I will try to understand, but if someone can go through their paper and do it and explain to me, I will also be happy. But anyway, this is not included in the lecture, so I will just, I think one application is enough, so we will leave it at that. Okay. Okay, so I will stop here. Yeah, sorry, I went over time, but as I said, only up to the previous theorem. That was all the lecture was.